Hey guys, I hope you are doing well. Happy Tuesday to you. One of the last Tuesdays of the year for you. So exciting. Anyway, as I mentioned in the previous day, the video or Loom or whatever that was, that I think was a Loom yesterday, we only have a couple topics left. And we're actually going to kind of end here today and tomorrow with one of the pillars of integral calculus, and it's called U substitution. All right, so we're going to hit this today and tomorrow, and then you're going to have a quiz on Thursday on indefinite integrals, which will include a lot of what we're going to do today and tomorrow. Follow along with the note sheet that I attached. These three examples we're going to do are on there, and nothing fancy. I'm just going to kind of show you how these work, and we'll take it from there, okay? So here's the deal. This process today is a process that allows us to evaluate indefinite integrals when they're more complicated, when it's not simply the power rule in reverse or undoing sine to get cosine or whatever it may be. But like, what do you do if it's a chain rule problem that you have to think of in reverse? That's kind of what this is about. So I'm going to show you the technique, and then I'm going to have you try a few, and I think you'll find the more you do, the more you get the hang of it, okay? Number one, first thing on every one of these, you need to establish U and then the differential of U, which is called du. So we'll get to that in a second, but how do I pick a U when I do one of these problems? And here it is. You want to pick something that is the inside function of a composition, okay? I'll say that again. Whatever you pick for U, you want to try to pick something that is the inside function of a composition. But here's the other part. Whatever you pick for U, you also want to see its derivative elsewhere in the problem. You want to see some form of its derivative elsewhere in the problem. So I'm going to pick for U cosine of x. Okay? Now, take a look at this. Cosine of x is the inside function for this exponential. And what's the derivative of cosine? It's negative sine, and that looks very similar, even though this is positive. We'll get to that in a second. Even though this is positive, that looks like the derivative of cosine, because that would be negative sine. So there I have it. That's the key. So now, what is du? So remember, we talked about differentials and how they're almost the same thing as a derivative, but instead of the dx being on the bottom when you write the normal derivative, you actually attach it over on the other side. So if I said to you, what's the derivative of cosine? You would say negative sine of x, but because it's not the derivative, it's actually the differential. That extra dx that usually goes on the bottom here is going to go over here. Every time, you're going to follow those same steps when you set up a U substitution problem, okay? Now, here's what we're going to try to do. We're going to rewrite this, but I want it to look identical to those two parts there. So if there's any little tweak I have to make, like, oh, this is negative, it wasn't negative before, I got to change that, okay? I'm also going to reorder it, and you'll see why in a second. But here I go. I'm going to write this as the integral of e to the cosine of x, okay? And then instead of times sine of x, I'm also reordering it, I just said that, but instead of times sine of x, I'm going to write it times negative sine of x. And of course, don't forget about your dx. Now you might say, whoa, Mr. Carnes, I get how you can reorder it. Obviously, you could switch multiplication, but how can you just add an extra negative that wasn't in the original problem? You can't unless you compensate for it. So because I wrote this as negative sine of x to get it to match this, I have to compensate for that by putting an extra negative out in front, and now the negative, it's the same thing we started with. So you're going to find, and I'll do that again in number 2, that when you rewrite it to look like these two parts, you may have something extra you have to do to compensate to get it to look like those parts. Now, watch the beauty in this. This is negative, the integral, and now because I got everything looking like these parts, I'm going to make my substitution. Instead of e to the cosine of x, it's e to the u. And instead of negative sine of x dx, it's simply du. Now look what I have. I have an integral, but it's much simpler now. And if I had to integrate this, that would not be a problem at all. Let's do it. The integral, don't forget that negative in front, the integral of e to the u would be saying, what's the antiderivative of e to the u? E to the u. The beauty in my favorite function, e to the x, is its derivative and antiderivative are e to the x. So this is an easy one. The antiderivative is still e to the u. And then don't forget your plus c. Now, obviously we're not quite done because I need to put the x's back in. So that would be negative e to the cosine of x plus c. This is definitely the kind of thing where you need to see probably multiple examples. So I'm going to go ahead and just do number 2. I mean, if you're real daring, go ahead and pause me and try 2 on your own. But I'm going to go ahead and do number 2 right now. What is the inside function? Well, for sure, it's 5 plus 2x cubed. Okay? 5 plus 2x cubed. But what is another reason, besides that it's the inside function, what's another reason that's a smart choice for you? Its derivative, which would be 6x squared, looks like the other part of the problem. Now again, I realize this is 1x squared, but the point that it's an x squared, that's what we're looking for. And so, yes, the derivative, or the differential, I should say, of 5 plus 2x cubed is 6x squared dx. Okay, hopefully that made sense based on our conversation on this earlier one. Okay, let's rewrite it, and I'm also going to reorder it while I'm doing it. So this is the integral of, and I'm going to go ahead and write, I always like the u part to come first and the du or dx part to come last. If you don't reorder it, it's not the end of the world. At some point you'll figure it out, okay? But I'm going to go ahead and reorder it, and I'm going to start with the u part. So this is the square root of 5 plus 2x cubed. And then times x squared, I'm actually going to write it as times 6x squared dx. Because remember, your goal, let me fix that, your goal is to get it to look like u and du exactly. Now you can't just change it from 1x squared to 6x squared without compensating. So what would kind of cancel out times 6? Times an extra 1/6. And now, the fact that I multiplied by 6 with this extra 1/6, they cancel out. There's no effect. It's the same as the original. Okay? Let's make our substitution. This is 1/6, the integral, square root of u du. Much, much simpler. Now, because we're going to be finding an antiderivative, I still think it would be easiest to change that square root to u to the half. And there we have it. All right, so now we're ready to integrate. Let's actually find the antiderivative. If you do the power rule in reverse for u to the 1/2, you have to add 1. So we know, first of all, here's the 1/6. So you add 1, you know that's going to be 3/2. And if you take the old coefficient divided by that half, so 1 divided by the 3/2, you end up with 2/3. And go ahead and try it. If you take the derivative of 2/3 u to the 3/2, yes, you get u to the 1/2. So there's our antiderivative. Of course, don't forget your plus c. Let's simplify that. That would be 1/6 times 2/3 is going to be 1/9. Let's put the u back in. What is u? U is 5 plus 2x cubed. Don't forget it's raised to the 3/2. And then don't forget your plus c. Okay? Now, if I had more space, I would actually take it one step further and rewrite it as a radical. So that's really going to be the square root of 5 plus 2x cubed. But I think you get what I'm saying there. That is an excellent example to demonstrate how you have to compensate when you change one part by doing something else to balance it with that other part there. So again, hopefully that made sense. All right, last one. I don't think there's a need to stop the camera and start again. I'll just go ahead and put this last one up. Now this last one is kind of tedious. Okay, so here we go. Number 3, the integral of cotan, I'm going by memory, I think that's what it is, of 7x dx. Okay? Now, you're going to find with trig that you sometimes have to use those identities that take you back to pre-calc. All right? You know, like for example, tangent is sine over cosine. Cotangent is actually cosine over sine. All right? So here's one where I'm going to help you a little more than I normally would, especially because it's our first day. I'm going to go ahead and tell you right now that u is going to be sine of 7x, which means that du is going to be, well, what's the derivative of sine of 7x? Well, it'd be cosine of 7x times 7 because of the chain rule, right? Don't forget that extra times the derivative of the inside. So this is actually going to be 7 cosine 7x dx. Okay? Now, you might be saying, whoa, how'd you know to do that? I would have never come up with that. Go ahead. What's the antiderivative of cotan? You don't know what it is. I don't know what it is. So because we don't know how to work backward with antiderivatives with both tan and cotan, it makes more sense to convert into sines and cosines. And how handy, because if you convert to sines and cosines, if you pick sine for this one, the derivative is some form of cosine. It's perfectly set up to be rewritten as the integral of sine of 7x. Whoops, not sine. We're not talking about tangent here. Cotan of 7x, cosine, third time's the charm, of 7x over sine of 7x dx, of course. Now if you rewrite it, that's not even calculus, that's pre-calc, but if you rewrite it like that, now we are perfectly set up that if I choose one part for my u, the other part is my perfect du. So that's a hard problem, definitely harder than the first two. That's why I'm just kind of giving you the u up front on one like this. But let's go at it. Here we go. This is the integral of, instead of cosine 7x dx, I'm going to call it 7 cosine of 7x dx, all over the sine of 7x, of course. And again, one more time, why did I write it like that? So it matches. Now, if you increase it by multiplying by 7, then you better compensate by multiplying by an extra 1/7. Now everything balances out. So this is really 1/7, the integral. Now, 7 cosine 7x dx is du. And of course, on the bottom, we have our u, which is really 1/7 the integral of 1 over u du. If I kind of slide that du off to the side instead of keeping it on top. Oh, now we're in luck. We know the antiderivative for 1 over a number. It's ln. This is 1/7. Now that I actually am ready to integrate, I'm going to go ahead and actually integrate. That's 1/7 times ln of the absolute value of u. Remember that from the other day. Plus c. And that means that our final answer is 1/7 ln absolute value of sine of 7x plus c. Whew, tough one, okay? One more time. You establish your U and DU. You rewrite your problem with those exact parts. Don't forget to balance it out with some kind of compensation if you have to. Then you substitute. You make it simpler, okay? And then you don't even touch the integral until you're ready to in this much simpler form. Then you integrate and you're on your way and you plug back in. So this whole crazy setup is simply so we can get it down to something that's a lot easier to integrate than what you see up here. A lot easier to integrate u to the 1/2 than it is this crazy thing we began with. So that's the idea. I think if you try a couple of these on your own, you're going to get better and better and better. Replay this a couple times if you have to, pause it, rewind it. I think this will start to click for you. Your homework is out of your book, one of our last assignments out of the textbook. I want you to try that for tonight, show all your steps, and then we'll chat again tomorrow. We'll try a few more of these. All right, have a good one, guys.